Hello, everybody. I hope that you all have settled down to hear the lecture. So, last time, if you remember, we saw the standard deviation of a. Today also we'll continue on data analysis part. And the standard deviation, last time what we saw is the standard deviation of a drunken walker from his starting point after n steps is given by, sigma root n. This is the standard deviation for a drunken walker after n steps. And the uncertainty in the sample mean, also we had seen that sample mean from n measurements is root n times smaller than the uncertainty of one measurement. To make one measurement, suppose your uncertainty is sigma, but if you do n measurements, then your uncertainty is sigma by root n. That is what we had done, this uncertainty in for a drunken walker. We had done this. If you remember, we did this xn. This is basically error on the mean by root n. I hope you remember this. This result is, amazingly general. It is derived we derived it for a random walk, and it is for discrete distribution. But exactly the same arguments holds for continuous distribution. And sometimes this information about sigma, which is the population standard deviation, is not known. But in that case, we can always take one of the sample standard deviation. So you can replace S with sigma, and if you delta x average, suppose you write a delta x, then you can write the standard error can be written as S by root n. Okay, this is what we have done. This basically what it says, if you increase your number of sampling, suppose one sample you get a certain value of xi. If you keep on doing sampling many times, then your mean value determination became more accurate, because uncertainty on your mean value shrinks. That is the idea of this study, and this is one of the very important equation in statistics. We will just make a simple example. We will take how using this we can determine what is the sample size we should take in a study. Let us take a situation where we are trying to study the effect of fertilizer in the production of tomatoes. So, okay. So what we have done, we have 5 plants we have taken, which contains, let me write down 5 plants. It gives 15 tomatoes with fertilizer. and we have another 5 plants. Sorry. With 13 tomatoes, where we have not used without fertilizer. And the average size of tomatoes in case of with fertilizer is 10 centimeter with a standard deviation equal to 2 centimeter. Whereas in case of without fertilizer, we have 13 tomatoes we have taken, but with a mean size is 9 centimeter with standard deviation equal to 2.5 centimeter. So this is the information we have with us. Then we will see really there is an effect of fertilizer on the plants or in the production or in the size of the tomato in this case. So what do you do? If I know in case of fertilizers, using fertilizers, let us define the standard error. That will be 2 centimeter divided by number of tomatoes, that is 15. Okay, just a minute. That's what we studied from our earlier study. Similarly, standard error and error for the case where without fertilizer is equal to 2.5 centimeter divided by. Okay, that is what way we have defined things. So this comes out to be 0.5 centimeters, and this will come out to be, you can calculate 0.7, and the typical means size is 10 here, and mean size here is 13. Here is 9. From this information, what do we see? That the size difference between the two cases, with fertilizer it is 10 and without fertilizer is 9. So difference is only 1 centimeter. And our standard error in this case is 0.5 centimeter and in this case 0.7 centimeter. So then what we see that our errors are 1.2, though our difference in our size in both the cases are 1 centimeter. So errors are more. So in this situation, we cannot make a decision. So then we have to revise our experimental design. So we have to suppose we want to make a measurement so that our uncertainty standard error for both should be less than equal to 0.5 centimeters. Now it is 1.2. We want to reduce that. If you do that, then what? How much number of tomatoes we have to take for each case? That is what we want to find out. So that can be written as 2 centimeter by root 10 plus 2.5 centimeters by root 10. This should be less than 0.5 centimeter. Okay. If you solve for n, it will come out to be 81. Okay. So that means if you want to increase your accuracy, what you have to do, you have to take more number of tomatoes. Or similarly, in a experiment, suppose you want to improve your accuracy, you have to take more number of sampling. So that is the bottom line. So in this case of n is 81. So maybe we have to, for each group, you have to take 30 plus because each plant in an average is giving 3 tomatoes. So you can take 30 plus 30, 60 plants per study. Where we have earlier we have taken only 15 and 13. That may not be ideal, but you have to take 60. So that is what we learn from here. That by taking more sampling or more measurements, you can get the required uncertainty in your measurement. This is just a example. So I just want to tell you. Okay, let me define something very interesting now. Something called is a very important concept in statistics. This is called central limit theorem. Everything and statistics will depend on this. When you combine n measurements, suppose there is a there is sample. So when you make a measurement, suppose n times, so you get x1, x2, so xn. So then you get a mean you can get just by writing divided by that. This mean, this value will be invariably different from the what is your original population mean. It is always, suppose you say your population mean is new, so your x bar will be different from mu. But suppose you do a many times sampling, so you will get a number of mean, this quantity. Suppose you make a sampling many times, then you calculate the mean of means, something like that, mean of means. So that will be sorry. So if you do this, what I wrote here, and this when you do mean of means, suppose you have sampled many times, then all these mean whatever you have got, again you are taking a mean of that. This new random variable this new random variable will have mean exactly what is the population mean. It will be mu, and it's a standard deviation. As we learned earlier, sigma by n root. Okay, n is the number of times you have done the sampling. This will be your result. If you take if your n is large, then let us see how things will look. You see graphically, but let us first understand in this way. Let me erase this. If you but if your n number of sampling is large, then the probability of taking the measurement and finding some particular value, suppose you are trying to take a mean of means, then you will get your mean of means is equal to your original population mean, and you will get a standard deviation which is equal to, as I told you, sigma standard deviation will be sigma by root n. And the distribution, whatever you will get from this, that will be something like this. Should be to the power minus x average to by 10. Suppose this using this, they will be distributed like this, and you can always find out what is the probability of getting particular mean value using this expression. And this can be also written. You can write this as a minus mu by okay. So what I am trying to say, when you study a distribution of average of various measurements, they will follow a distribution which is called the Gaussian or normal distribution, and they will have their uncertain standard deviation will be something like this, sigma square by r. Instead of standard deviation sigma, they will have their standard deviation something like this, and this is what is called the central limit theorem. That means when you do your mean value you measure from a system, distribution of means will follow always a Gaussian distribution. Let me explain this more in a pictorial way. Suppose we have got two initial distribution. This is important, what I'm telling now. This is 0, this is +1, This is -1. And there is another distribution. So 0 +1 -1. Suppose I have a distribution. And there is another distribution, something like this. That is two peaks and one peak. This is my population distribution. Then over this, if I carry out measurement and I want to measure the, suppose I carry out measurement, maybe 10 events I will take from each and then find out what is the mean value. Similarly, if I take like that, if I take suppose certain mean value I will get, then again I will take another 10. Then I will find that mean value and another 10. Like that, if I do, suppose I do for 4 times, and I plot the distribution of mean values 0 +1 -1. So in the single peak case, it will be more or less Gaussian. Maybe my figure is not coming very nicely, but it will be. We assume that is a Gaussian normal distribution, and your mean will be same as the your original population. But maybe in this case, initially, it may give you a distribution something like this: 0, maybe something like this. But when you go on taking more and more measurements, and then you add all those values, and then you plot what you would say. Suppose I am taking an extreme case. It will look like this. In this case, it will be slightly. They are normal distribution. I'm not able to, but assume these are normal. Similarly, in this case, also. So what I'm trying to drive home is what may be your initial distribution, but if you make a mean of the variables, their distribution will be always a normal distribution. That is what this expression says. So whatever may be your initial distribution, it may be 2 peak or 1 peak or many peaks, but when you make multiple measurements and you want to plot the mean of those values, then you will see it will be always a normal distribution. And more measurement you do, more sampling, then your width will be. That means your uncertainty on your mean value determination will go on decreasing. So that is that we want to drive home this information. This is a very important concept. Let me emphasize once more. What I am telling, your initial population distribution may be single peak or double peak. But if you want to measure mean value distributions by doing n number of sampling or n number of measurement, those mean values distribution will always follow a normal distribution. and its a standard deviation will go on decreasing as n increases. Okay. Okay, let me. This is one of the very important concept in statistics. Most of things will depend on this. So, which way we can use this information? How we can use? We'll see now. So we know that the probability of once you know that the probability of measuring a sample mean is given by a normal distribution, because when you do n number of measurement on a particular population, its mean distribution will always it's a sample mean is given by a normal distribution. So let me once more write that expression will be using. The normal distribution means you will get something like this. Let me write that. Let me rewrite that expression. You may be using. Or yeah, let's see. So what, how we can use this distribution, we'll see. So once we know that the probability of measuring a sample mean is given by a normal distribution, we can use this knowledge to test hypothesis, our research hypothesis, and find the precise likelihood your result come about by chance. We can suppose we want to know particular mean value, like this x average. What is the likelihood of that getting? So that type of thing we can do by simply slightly modifying this expression, where you can substitute z as a variable, that is x average minus mu by delta x. You will substitute this one on our this expression, then what we will get is Ez equal to 1 by 5 or minus z square by 2. Why I did this? This is a function which is normalized to 1 with its standard deviation is also 1, and it will integrate it from minus infinity to plus infinity. This will be 1. So this is basically a normalized normal distribution. So if I plot it, it will look like this. 0, Z. This will be a normal distribution. And there is interesting thing is that suppose you want to find one sigma, one. What is the area? 1 sigma or 2 sigma? You could plot that. Z value, suppose Z value 1, Z value 2, and this is your cumulative probability between the minus Z and plus Z. If you plot, it will somewhere 1, but it will be like this. One Z will be some 67%. 2Z will be almost like a 99% of the 1. So this also helps us to find out. Suppose I have some measurement, I can know it should follow a normal distribution. Any measurement. Suppose I get I will try to find out what is the probability of getting Z value equal to 2 or more. So that probability is corresponding to the area. Total probability will be area of this and also area this side. And when you do hypothesis study, there is a general consensus that if your probability is less than 5%, then you say my null hypothesis is not correct. So that is how again you use these distributions to test your research hypothesis. Maybe we'll take a few examples so that will give a better picture. Let me erase these things now. Okay. Let us see what is. I will take another example to show you how we can use this to understand actually what is going on. Okay, let me take one more example. Let me first define what is the hypothesis testing. In a hypothesis, we know that there must be one, there must be one independent and at least one dependent variable. Dependent variable is what we will measure in a experiment. It is the dependent variable that we will measure. And once you have settled on an independent variable, you can state the null hypothesis. The null hypothesis is usually that changes in your independent variable will not change the dependent variable. So your null hypothesis, the null is usually that changes in your independent variable will not lead to any significant changes in your dependent variable. No, in a hypothesis, you have one independent variable and one dependent variable. So normally you change your independent variable and then see what change it brings in the dependent variable. That is the hypothesis testing. But always you define a null hypothesis with the assumption that there is no significant change in your dependent variable while you are changing your independent variable. And the hypothesis that changing the independent variable does change the dependent variable is called alternative hypothesis. And the alternative hypothesis is the hypothesis that changing the independent variable does change the dependent variable. Now, null hypothesis is always, you say there is no change in the dependent variable while changing the independent variable. But the alternative hypothesis or the research hypothesis is called when changing the independent variable does change the dependent variable. It is called alternate hypothesis. And always it is you have to see whether null hypothesis is valid or not. When null hypothesis is not valid, then automatically you say that alternate hypothesis is valid. So that is how you do hypothesis testing. So we'll just take few examples and see how it is working out. Suppose, okay, we'll do it in two ways. Same problem, we'll attack in two ways. First, we'll see how just doing the error analysis, we can come to a conclusion, and then we'll do how we can do the same thing by doing Z statistics, what we defined earlier. So let me first do with the error analysis. What do we want to do? We want to see the fairness of a clipping of coins. We know that if you clip coins infinite times, then the fraction of head converts to 0.5. If you infinite number of times if you toss the coin, then the probability of getting a head would be 0.5 and probability of getting tail is 0.5. But you want to do experiment where you have taken only 100 flips, and you got 46 heads and 54 tails. The first thing to study this, whether it is a fair coin or not. But the idea is that you will see whether statistically 100 flips can give such a difference from the for infinity case. You should get 0.5 instead of 0.5. If you are getting anything different, then you have to see whether it is just coming due to uncertainty of the process, or there is a genuineness. It is not a fair coin, that it is biased. That is what we want to find out. So first, what we will do, we will find the average. Let's say head means 1 and tail means 0. So your average will come. Here you will getting average is 0.5, but you will get average equal to 46 ones plus 54 zeros divided by 100. So that comes out to 0.46. So instead of 0.5, the average value you are getting now 0.46. So then let us calculate the sample standard deviation. So sample standard deviation is calculate 46 to 0.46 square. So this is your average, experimental average is 0.46 plus 54 into 0 minus 0.46. Okay. Degree of freedom is now 1 less, 99. To do this you get. Oh, sorry. Should be point. Then what is the standard error? Standard error is for this is this or delta x is equal to S by root n. So S is 0.501 divided by 100 root 0.0501. So you have to plot, suppose this is 0.5, the mean value. This is expected. You expect it should be 0.5 mean value after infinite multiply. But experimentally, what you are getting is 0.46 like that. It's error bar of 0.05. So error bars are expected values. These are the error bars. Therefore, there is no ground to reject the null hypothesis. Null hypothesis is, what is the null hypothesis in this case? You say that they are pair. There is no difference between these infinity flips and 100 flips. And alternative hypothesis in this case is that no, there is a bias, so I'm not getting. I've got only 0.46 average, not 0.5. But one can see that these two values are overlapping because within the error bar. So you can say that null hypothesis is valid, and it is consistent with because of the nature of the flipping of fair coin. If you do 100 flips, there is a probability your mean should be 0.46. So this is what you can do just from error analysis. Same thing also you can do from Z statistics, what I earlier you told. So let me do that for you also. So in Z statistics, you define Z, then add your average minus mu divided by your standard error. So in this case, your X average experimental was 0.46 and your infinity case, your average should be 0.5 divided by your uncertainty we calculated just before, that was 0.0551 or something. This gives a value 0.8. Suppose you go to you plot now Z, which is 0, this is 1, 2, plus 1, 2. So what has been done now? You are trying to plot from the expected mean value, your measured mean value, how much it is different in the units of your error. Okay. So then your Z value you are getting one is 0.8. It will be somewhere here. So it is less than 1 sigma. No? But maybe so you will see what is the area here and what is the area beyond uh, beyond this shaded region. And if you are getting a value anything more than 0.8, that is what is the percentage. That means you get there are Z tables which will give you what is the area total probability between minus Z to plus Z. And if you make 1 minus that, then you can see what is the remaining probability from 1. So 1 minus your probability Z will give you the remaining area, like these areas. So in this case, if you see the Z table, you can find for 0.8, your probability for the value Z value greater than 0.8 is coming out to be probability is 42%. So that means for 42% at times, just chance can give you, value more than Z point Z is equal to 0.8. So because of that, earlier we saw that due to overlap of the error bars, we can say that we cannot reject the null hypothesis. Similarly, yeah, you have now a probability. Almost 42% are remaining for values greater than 0.8. If that is the case, so as I told you earlier, that our null hypothesis we can only reject if it is 5%, but now it is 42%. So we cannot reject the null hypothesis. So that means the final conclusion is that when if you have done 100 flips, the coins are fair, and it is expected that for 100 flips you can get a mean which is 0.46 instead of for infinity throws. That we expect is 0.5. So there are few more examples we can help as we go along. Next, we'll solve few more examples. Today we'll stop here. So I would like you to ask questions, and any doubt, then we can discuss. Name? Yeah. Which one, you know? Which book you should follow? Okay. I'll tell you the book. Research methods for science. Can you write even this? Search methods for science. Science. You write Murder. MP Murder. M E हाँ ओके ओके क्या बोला मेरा बात है तो क्या जब थोड़ा आप जाएंगे इधर okay so कुछ क्वेश्चन है please share the notes okay sir can you please elaborate okay okay I'll just explain again the plot तो दिखाइए तो plot So what I have done, suppose you have a plot. This is suppose expected. This will be 0.5. So you will have point here. If it is infinity flip, then your mean should be 0.5. So it is here. But what you have got now in the experiment, observe. Observation is giving 0.46. Right? That is what average value we got. So 0.46 means I will 0.5. Suppose this is, let's say this is 4. So this will be 0.45. This is suppose 0.4, 0.45, 0.6 will be somewhere here. So your point is you are getting here. And this has a error of, we calculated what is the standard error, that was 0.05. 0.05 means half unit you will go 0.05 means this much is your error plus and minus. So I took it up and also down. So this is 0.46. So my end point will be 0.46 plus 0.05. So 1.511. So it will go above 0.5. Okay. Sorry, 0.511. So this value is now 0.511. Mm-hmm. 0.5, slightly more than. Okay. So I hope you got that is what I wanted to tell, because your expected value was 0.5 and your observed value with error bar is falling within that. So because of that, you cannot rule out the null hypothesis. Okay. Okay. Sir, rejection criteria 5%. Okay. So, yeah, maybe when you solve some more problem, it will be clear. So let us say I will make a Z plot. 0, 2 minus 1 2 something like this. So basically what you are trying to see, how many standard deviation your data is away from zero. Suppose you are away from zero, suppose your Z value you calculated, it is coming out to be more than 2, let's say. So more than 2 means your probability, if you will calculate for 2 and more, what will be the area under the curve? Because this area is, total area is 1. And similarly, you can calculate for this side how much area is. So I know that whenever it is 2, Z is equal to 2, if you can look into the Z table, you will see, like, we normally know, suppose 1 sigma means 67%, 2 sigma is 97%, 3 sigma is 99%. Similarly, here 1.96 Z equal to 1.96 will cover the area what is the 95%. So that means for Z value minus 1.96 to 1 plus 1.96, that area it will cover will be 95%. Suppose you are getting a value anything beyond that, then you can say they are falling within 5%. So if your value is more than 1.96, when you are comparing two means, if your Z value comes out to be 1.96, then you can reject your null hypothesis and you can say the alternate hypothesis is correct. So that is the thing. So we'll solve few more problem, and then maybe because once you solve problem, then the understanding will be better. Which question? Yeah. Will the error bar height will be small for large sample size? Yes, that's correct. Suppose more number of times you do measurement, that is what we saw, that sigma by root n will be your standard error. That means more number of times you do, it will reduce your error and your mean value will be more well defined. That is what we also did for random walk and also in our other case. और कुछ क्वेश्चन है दूसरा में? ठीक है. Okay then, thank you all. See you next time.